they will do the same thing every time, okay? It's friction is what kills repeatability I told you about earlier, okay? So imagine you have this 4-bar with these pin joints, these revolute joints, and it's attached to a spring, okay? And you load it with a force here, and this moves over a displacement x. Well, every time you load it and then unload it, thanks to the spring, it's going to spring back to the same place it started. But what's going to happen is if you plot the force versus displacement, it's going to go up a certain load. But then when you lower the force, so drop it back down to 0, it's going to go unload along a different path. And the reason is because, like, look, the work you put into the thing in the loading path is the area under the red line here, okay? Now, you know, a lot of that energy is stored in the strain energy of the spring, which is why it recovers. That's actually the area under the green curve. The reason they're not on top of each other is because there's a lot of friction, there's a lot of energy lost and dissipated at the rigid joints, okay, through sliding contact. So it generates friction, and that energy has to go somewhere. So, and that energy that's dissipated is the area in this little sliver. It's called a hysteresis loop, right? So the total energy recovered from strain energy plus that dissipated energy is the work you put in, okay? And so anytime you get this, so anytime you have a rigid system with sliding joints or anything that's generating friction, you're going to have some degree of load path and unload path that do not correspond, and you're going to dissipate, you know, heat and energy, and your surface every time you go back and forth is going to be different. So it's going to have horrible repeatability, and this is called the hysteresis loop. Now, hysteresis occurs when to know the state of the force and displacement, you have to know the history of its loading. So for instance, if this just loaded up and down along the same red path, then every time I said it was at this displacement, you would know it had this force. Okay? And you wouldn't need to know about how many times it was loaded and unloaded. You wouldn't need to know about its history. You could always map any displacement to any force. But in this case, if it goes down a different path, then, you know, if I said, okay, I'm at this displacement, well, you'd have to know, are you unloading? Because that would be the force. Or are you loading? Because that would be the force. There's two different forces it could be. And to know which one it is, you have to know the history of the loading. Has it been loaded? Has it been unloaded? And by the way, every time, if you did this over and over again, the loop would be slightly different every time. The hysteresis loop would change a little bit. It might settle into something, but it's going to be different every time. So depending on, and I should show this, you know, loading and unloading, it's like a different path every time. Because of the friction. It's not repeatable. It's a piece of junk. And you know, it's going to dissipate all kinds of heat. And you need to have a knowledge of the history of loading to know the relationship between the force and displacement, okay? That's not good. If you have flexures and you elastically deform it, it's going to go up and down the same path repeatably with no change. You'll always know the state. You don't need to know the history. And it's not going to generate friction. It's just going to spring back, and everything's going to be precise, okay? So friction, hysteresis, these things are anti-precision or repeatability. They kill it all, which is why compliance is so awesome. Okay? So just as a rule of thumb, you know, well, first of all, let me teach you about yielding. You can load something large enough that it surpasses the yield stress, and what happens when things start going above yield stress is the atomic bonds start breaking and reforming next to their neighbor. And that releases energy that manifests as heat. You know, if you get a hanger and you deform it back and forth, plastically deform it, it gets very hot. And it dissipates heat. That's from the atomic bonds breaking and reforming. And that's internal friction. And that will manifest as hysteresis and all kinds of things that's bad. So materials, just because it deforms doesn't mean it's precise. If you deform it too far, it remains permanently deformed. You can see we're stretching here. There's like a dislocation. Not only do the atoms break and reposition, but there's a whole dislocation, a slip plane of them that propagates through the material. And then when you unload it, it does spring back a little bit, but it remains permanently deformed. So if you take a hanger, deform it, plastically deform it, you let it go, it'll spring back a bit, but it won't be straight again. Okay? So then you'd think, well, from those principles, just don't yield it, and it'll be repeatable. Well, the truth is there's always micro slip. You know, it's not that everything's perfect until yield strength. It's a little gray area. So if you want to achieve like picometer precision, it's a good thing to design it so nothing ever gets stressed above 20% of the yield strength as a general rule of thumb. If you do that, then you're going to be pretty safe. But above 20% yield strength, there's little microslip. It's just lots of slip occurs, yield strength and above. Okay, so, the other way, don't yield, if you want super high precision, don't allow things to go above 20% yield strength, okay? The other thing you can do is be sure your load direction magnitude are repeatable, right? I mean, it would be really stink if you designed your flexures to be super repeatable and amazing to get picometer resolution, but then you use like a lead screw actuator, which generates a bunch of friction as the lead screw rotates in its bearing. And that actuator is not repeatable. So make sure your actuator is high precision, that's going to push the flexure, and make sure its load direction is repeatable. Every time you push on it, it doesn't change something about it. It always pushes in the same direction and same magnitude in a repeatable way. So make sure your actuators are precise too. By the way, one good way to make actuators precise is to have no contact actuators. So like a voice coil is a great actuator. It's basically a cylinder that's a magnet and then a coil wire wrapped in it. And if you run current through that coil wire, it makes a magnetic field that can drive the cylinder back and forth with a force, and nothing touches. So since nothing touches, there's no friction generated. It's a very precise actuator. Okay, so you want to use actuators like that are very precise. Okay? So another thing to think about is, like, of course, the best flexure would be to make something out of a material that's just a single piece material. You don't have to assemble anything. Okay? Because honestly, joints, there's all kinds of slip at joints that create friction, and that's bad for repeatability. So the less joints you have, the less you join two things, the better. So if you can make a flexure out of a single piece of material, like CNC it or something, that's awesome. The other thing is if you can do single crystal, there's often microslip at grain boundaries if you zoom into metals and stuff. And you can get rid of like micro friction, slip if you don't have grain boundaries. It's just everything's a single crystal material. I mean, then you're talking picometer resolution stuff. So single crystal stuff that's one material. Then you got incredible resolution. That's and make it yield it so or load it so the stress is even below 20% yield. That would be amazing. Okay, but you don't always have that luxury. Sometimes you have to make it in planar pieces and then assemble it. Okay, so there's some rules of thumb to assemble things. Okay, so this is from Alex Slocum's book. He wrote a great book on precision design. Okay, and if you assemble this flexure onto this, some people may not put these clamp blocks. They just might put two bolts and be like, okay, we're good. Not a good idea. If you put clamp blocks on top and then you put the bolts through, they spread out the strain and the stress, and it'll dramatically improve the joint so there's not that micro slip when they deform. By the way, the other bad thing about flexures is when they deform, they always deform with the highest strain at their base, at the top or the bottom, right? Or the top here or the bottom here. And that's usually where the joint is. And so that's bad, but I'll talk about how to fix that. But going back, not only do you want to use these blocks to spread out the stress, but, and by the way, you can use glue in there too. Use glue, use the clamp blocks. That helps get rid of the microslip of the joint. But the other thing is you need to use enough bolts. If you're going to put bolts in there, and first of all, you need to understand what strain cones are. Say you're joining two materials together, the red and the blue, and you put in the bolt. Okay. Once you clamp it down, the shank stretches, but the material gets compressed, and there's a strain cone that comes out from underneath that. You can barely see it here, but it's a pink kind of color that comes out at a certain angle. And depending on the material and depending on the force and everything, you can control that strain cone. But it's what it is. There's a strain cone here, and then there's a strain cone that comes from down here and meets it from the bottom threads on up. Okay. So if you don't use enough bolts, if their strain cones are spread so far apart that they don't touch, right? Then the surface is uneven because there's a strain cone that's bulging from Poisson ratio, right? And this interface, there's going to be opportunities to slip. This is, by the way, when you're designing a gasket, joining two parts and there's pressurized fluid inside, you don't want it to leak. You definitely want to use a lot of bolts so the strain cones touch. If you have two neighboring bolts, you want the strain cones where they terminate to touch so that the strain is uniform all the way around. So there's no gap for the gas to leak out. Well, it's the same thing with microslip. You might think, well, it's overkill to put so many bolts in this because it doesn't need to be that way, but you need that so the strain cones touch. Now, if they overlap, it's the same problem. You don't want too many bolts that overlap because then the interface will also undulate with the Poisson bulging, right? And you'll get microslip as well. So, you don't want them too far apart. You don't want them too close. You want them just right so the strain cones touch and that strain is uniform. Then there won't be microslip. Okay, so glue, clamps, and strain cones touching is the best you're going to get at assembling these things. The other thing is, like I said, recognize that most of the strain is going to occur at the ends here. And that's a problem because you don't want the strain occurring near a joint. Okay, for this design, I don't know if you can see it, but there's a stage and a ground, and then I had these little flexures that were cut with two rectangles, and then the flexure is all one piece, and I put two bolts to join that piece onto this. If I didn't, you see this little tab here? If I didn't have that little tab, and I just had this wire connect directly in there, then it would deform right there, okay, which is at the interface of this piece and that piece, which means it would make microslip. But if I put this little tab here, and I basically terminate the base of the flexure here, then this is much stiffer, and most of the strain will occur right there, which is above the joint. Okay, so you can use these little tricks to artificially raise where the max strain is, and take the max strain and move it away from the joint, because you don't want microslip, or it'll kill your precision. Okay, so this is a little exercise to prove to you that flexures, you might intend to make them accurate. You might design it so that it has just the stiffness you want, so that when you push on it with just the force you're going to push on it, it deforms and gets right. The actual thing is going to be the intended target, right? Well, with all your best intentions, it's never going to get the actual target. You have to calibrate. And here's why. So just take a simple flexure that's width B, length L, and thickness H, okay? Say, by the way, the stiffness of this, if you push on this with a force here and it displaces, the relation between the force displacement is the stiffness, and that's E, the modulus, times B H cubed divided by 4, 3 cubed, okay? And you can look that up. That's just beam bending theory. So that's the stiffness, and you could say, okay, well, I want to design that stiffness. So you carefully calculate the B, the H, the L. Problem is look how sensitive the stiffness is to H and L, right? It's to the third power. So if H is off by just a hair, it's going to be way stiffer. And if L is off by just a hair, larger, it's going to be way less stiff. Okay, so you need to be very careful. Like, there's tolerance that occurs. Like say you get a machining process, you're going to machine this. You need to look at what's the tolerance of the machine, and if the machine can't cut it, it can guarantee you some H plus or minus some tolerance, or L plus or minus some tolerance, or B plus or minus some tolerance. And if you stack all that up, which I'll do in a second, I'll show you an example, you'll find that even with tiny variations in these things, because it's so sensitive to H and L in particular, but it's also sensitive to B by 1 power, you're going to get a different stiffness than what you designed for, whether you like it or not. And then even your force is not going to be exactly what you want, and it's probably not going to be in the same direction, right? So that's the other thing, actuator alignment. So not only is it tough to get the parameters exactly how you want, and it's going to change the stiffness, the actuator you're never going to be able to align it perfectly, okay? And then the other thing to think about is there's time-dependent things. Like, this material will expand if it's heated, usually, if it has a positive thermal expansion coefficient, right? So you may not take that into account when you design it, and then suddenly it's a different temperature, and it'll get to a different spot. or there's creep and stress relaxation, right? Creep is a time-dependent error, or time-dependent phenomena. It occurs when you load something with a constant force, and sure, it deforms initially when you load it, but then over time, as you maintain that force, it starts to displace slowly and creep. That's a time-dependent property. Stress relaxation is kind of the opposite. It's instead of applying a constant force, you apply constant deformation. Like, so say I just put like a big ball under this and deform this up and keep it deformed at the same curvature over time. Initially, there'll be a bunch of stress in the beam, but over time, if it stress relaxes, then that stress will go down, and then when you remove the ball, it'll remain permanently deformed, right? Those are time-dependent issues. And just so you know, anytime a material starts approaching half of its melting temperature, the material kind of starts behaving a bit like a liquid, which adds some viscosity, which is where you get these time-dependent errors. So creep and stress relaxation become a big deal. Polymers, you almost never make flexures out of polymers, because even at room temperature, polymers are creeping and stress relaxing all the time and generating all this internal friction and hysteresis. So polymers are not a repeatable material. They're made of all these chains of monomers like spaghetti, and when you load them, they slowly start slipping past each other, and that's internal friction, and it's a big problem, right? So metals are usually great, but even metals can creep when they get hot enough. So if you want to eliminate creep and time-dependent things, you can keep things really cold and use metals, and you usually don't have to worry about it, okay? The other thing that could throw off your accuracy is dynamics, vibration. This could vibrate. Maybe you load it too fast and it kind of overshoots and vibrates, and that can throw off getting the intended to align with the actual, okay? So no matter your best efforts, all these points I've made on this slide is like, look, good luck making the flexure to achieve the actual location you want it to. You're not going to get it. So just make it the best you can. No matter how you make it, it'll be super repeatable as long as you don't yield it and follow the principles I taught you. And then just calibrate it. It's like tell the archer to start aiming in a different place. And once you calibrate it, it'll be both accurate and precise. Okay? So here's the example where I told you, like, pretend, so the stiffness of this beam is K equals EBH cubed divided by 4L cubed, right? And say you designed it to be that H, L, and B. Well, now say you have this tolerance where you were 5% off plus and minus an L, 5% off plus and minus an H, and 5% off plus and minus an B. How much in the worst case scenario, if you fabricated this with this bad of a tolerance, would the stiffness change? What's the worst case max stiffness it could be minus the worst case minimum stiffness it can be, and how much could that stiffness change from what you wanted? Okay, well, I won't go through the math here, in terrible detail, but you can look at it because you have these slides at home. But you can imagine the max stiffness would be B plus delta B, okay, because it's in the numerator. You want that to be large to be the max. H plus delta H, again, it's in the numerator. You want L minus delta L because that's in the denominator. You want that to be small, so this is as large as possible. And then you flip the signs for the minimum. Okay, you plug those in and subtract them to find K max minus K min to make delta this, and you find, my goodness, it ends up being 71% of the intended stiffness. K. So it could fluctuate just by having this 5% tolerance issues. You could vary somewhere between 70% of the intended stiffness. So you're not going to get the actual. Okay, but that's okay. Calibrate. Okay. So now let's look at flexure issues, things you'd want to consider when designing flexures. Okay, so thermal expansion is something to take into account. I mentioned this before. Every material has some kind of thermal expansion coefficient. Okay, some materials are close to zero, like Invar is a really low thermal expansion coefficient, so you don't need to worry so much about thermal expansion with that. But most materials, if you heat it up, some delta T, that's some change in temperature. It has some thermal expansion coefficient that if you times it by that delta T, it'll tell you the strain, how much that material will strain. Which, of course, strain is change in length divided by the length. So if you times length by this stuff, you get how much it deforms. So think about it. If you take this flexure design, say it's grounded, it's pinned down at the circle, and you heat the whole thing up, and it has some positive thermal expansion coefficient, well, then in truth what it's going to do is it's going to rotate. And if it rotates, then that's a motion you probably didn't want. And that's called, it's now said to be thermally unstable. Okay? So basically something's thermally unstable if when you change the temperature, it drifts in some unwanted direction. That's the definition of thermally unstable. So you could make this more thermally stable by making it symmetric. Okay, if you make it symmetric, so add, instead of having just these things on this side, you add it in all the directions. Now it still gets the same degrees of freedom, but when you heat it up, this stage will largely not move. Now it will still move, right? These guys will start expanding, and they'll kind of buckle, and they'll kind of rotate and do weird things, but it's much more thermally stable than the previous design. It won't do this awful large rotation. It'll just do these tiny little tweaks to accommodate the buckling of these things, okay? So that would be considered thermally stable. And again, there's not some hard cutoff, but it's just more thermally stable than the other, okay? So let's look at these examples. You got to ask yourself, is this thermally stable? Well, if you ground this, and this is the stage, you heat this up, these guys will expand and this guy will move up. So this is not thermally stable, okay? Okay, so that one's not thermally stable, okay? So this one, say these are the ground, and you heat this up. Well, this guy will be about as thermally stable as this. These will expand, they'll try and buckle, they won't be able to move much. This guy's not going to move much. It will move a little bit as these buckle, but it's largely thermally stable, okay? Let's skip to this guy. This guy is grounded here, and when you heat it up, it'll drift over, it'll move this way. So this is not thermally stable. So these guys are the guys that aren't thermally stable. This one is thermally stable, and it's the most thermally stable, and here's why. So these guys are grounded. These are intermediate bodies, and that's the stage. If you heat this up, these guys will grow, but these guys will also grow. And so if these guys will accommodate these so they don't even have to buckle. So this stage, it's moving because I'm showing it actuating, but if you just left it be, this stage would largely not move at all, and there would be no frustration from buckling. Okay? Now, there would be a little bit because this is shorter than that, and according to this, the change in L of this will be less than the change in L of this, so there will be a little buckling, but you could fix that by, if you cut this stage in and move this inside of it and give it room for its range, so that the lengths of these are the same, then it's perfectly thermally stable. As long as you uniformly heat the whole thing, the stage isn't going anywhere. Okay, so think of that about that when you're designing precision. Small motion machines that are moving atoms and doing, controlling light and doing things that require high precision and accuracy. Just assume things are going to expand or contract as temperatures change, and design the topology so it's thermally stable to account for that. Okay? So you also need to consider vibrations. Vibrations are always occurring, okay? And you need to understand the fundamentals of vibration because they can mess up your machine, right? So look, to understand the fundamentals of vibration, imagine you got a rigid stage here connected by a flexure onto another rigid stage here, okay? And say I take this and I shake it with some input with a magnitude A, a sinusoidal thing, back and forth cyclic, with a natural or with a frequency of omega with time t, right? So I give it some sinusoidal input displacement. Well, what's going to happen if I plot the gain, which is, okay, so first of all, the output of this will be the same amplitude times some gain, times the same sine, times the same frequency, times t plus some phase. Okay, so it's basically the same as the input, but we now add a gain to change the amplitude and some phase parameter to get it out of phase. Okay, and if you plot the gain versus the frequency, you get what's called a Bode plot. There's also phase versus frequency, but I'm not showing that here because the gain is more instructive. Okay, you'll find it looks like this. There's a frequency that when you shake it, all these frequencies from here to here essentially, as you shake this back and forth nice and slowly, this will be stiff enough that this will be able to respond. The gain will essentially be just 1. Okay, so as you move this back and forth, the top will move right with it at slow frequencies. Okay, but then it reaches some point here, which is the natural frequency of this body. The natural frequency of that body can be calculated by taking the stiffness of this flexure dividing it by the mass of the stage and square rooting it. That's the natural frequency. We'll prove where that number came from later, but that's what the natural frequency is, okay? And that's the point where if you start driving it at that natural frequency, it becomes in resonance, and the magnitude just goes through the roof. This is how, you can break a bridge. If you get all your buddies and walk with the same natural frequency as the bridge, it'll resonate and break it, because the gain goes through the roof and the output will just cause the bridge to move way further than it can, and it'll break, okay? So this is called the bandwidth. The region between this, the natural frequency, and this is the range, or the frequencies that you can drive it and it'll do what you want it to. The output does what the input tells it to. Above that, it'll break itself, or it'll start freaking out. And if I actually plotted the phase versus frequency, you'll find it gets out of phase by a certain amount, depending on how it's designed, right? So suddenly you start moving this back and forth fast enough, and the M will start going the exact opposite direction with huge output magnitude gain, and possibly break itself, right? I mean, sometimes it doesn't break itself, but it'll start freaking out, and it will be out of phase. And you don't want that, okay? But then you find as you go even faster, it just suddenly drops off and just goes away. So this almost becomes zero. So basically, you can imagine there's a point where this moves so fast that just sits there. It doesn't even move. It can't even respond. It has so much inertia that this little wire flexure can't accelerate it, and it just sits there, okay? So you need to understand most Bode plots look like this, okay? That for like a nice second order system, mass stuck on a spring, if you're loading it with a force or displacement, okay? So that's what they most look like, and that's a fundamental principle that we'll talk about in a second, okay? So you need to understand mode shapes, though. This is kind of a one-dimensional Bode plot, but in truth, everything is in 3 dimensions. And this is like an example. Say you have two bodies here connected directly together by wire flexures, and I start shaking it, okay, at different frequencies. Well, you need to realize when it's not a one-dimensional system, if it's a 3-dimensional system, there are infinite natural frequencies, okay? There's the first natural frequency, omega 1, and then there's a second natural frequency, a third natural frequency, they go up to infinity, okay? And each natural frequency is associated with a mode shape, okay? And a mode shape is essentially how it deforms at that frequency. Okay, better definitions is directions in which exchange between potential and kinetic energy is most favorable. It's basically the shape it makes as it freaks out, right? Or a non-controlled oscillating motion associated with this direction. Okay, so for this design, okay, and you can just CAD these and do a frequency analysis, and it'll tell you the mode shapes, and it'll tell you their associated natural frequency. So here's the first 4 mode shapes, and here's the 4 corresponding natural frequencies, okay? So the way this works is, imagine I grab this end and I start loading it back and forth in the direction of the first natural frequency. Well, what'll happen is, you'll get a gain of 1, as usual, and then when you hit that first natural frequency, it'll freak out with a huge spike, and then it'll go down. Now you'd think, well, hold on, if I still keep oscillating, if I grab that and oscillate in the direction of the first natural frequency, how could the second mode shape be excited? Well, it does. There's always crosstalk. And so what will happen is, in reality, as you get down to the second natural frequency, there'll be a little blip. It won't be huge because you're shaking in the wrong direction. Okay, but then when you get to the third natural frequency, it'll move with that mode shape. It'll be another little blip. And then the fourth mode shape, another little blip, okay? But if you now say you took the first body and you shook it up and down in the direction of the second mode shape, well, then what's going to happen is you'll get this plot, you'll get a nice blip here, not as big, then you'll get a huge blip here, and then you'll get your little blips here. Okay? So you can see, yes, the direction you shake it matters. You'll get a bigger blip in reality, but no matter how you do it, as you approach the natural frequencies corresponding to the mode shapes, you'll get blips of different sizes, okay? Where it wants to freak out, okay? And mode shapes are like, you can see a bunch of videos about mode shapes. There's like, if you get a rope and shake it back and forth really quickly, it makes a smiley and a frowning face. But if you shake it faster, it starts looking like a sine wave. If you shake it faster and faster, the rope starts, having more undulations in it. Those are mode shapes of a very simple string, okay? But all 3-dimensional structures have mode shapes and infinite natural frequencies corresponding with each mode shape, okay? Okay, so that's just general hand-wavy principles of dynamics, okay? But the thing to take from this is principles for how you minimize vibration.